Welcome to section 9.7. We're dealing with probability. You will be happy to know this is the last video for pre-calc, so enjoy it. The easiest way we are talking about probabilities is to list the outcomes. Now, we listed outcomes when we were in Algebra 2. What we didn't call them, though, is what we call them in pre-calc. And the biggest thing is we call them the sample space. And so we want to look at what is the possible outcomes. So let's start with the first example. A coin is tossed 2 times, and the results are recorded. What possibilities could you have? And the way we write it is a set notation. I could roll a heads, or a flip a heads for the first one, heads for the second one. I could do a heads and then a tails. I could do a tails and a tails, or a tails and a heads. And so if we look here, as you go through the probability, there are 4 outcomes. And we need the number of outcomes in order to find a probability. Now, probability is always as a fraction, and I would prefer the fraction unless they start you in decimal mode. But take a look. What is the probability that both are heads? Well, if you look, only 1 out of the 4 are both heads, so my probability is 1/4. Okay, so let's try again. First I roll a die, then I toss a coin. Okay, so here we go. I could roll a 1 and then get a heads, or roll a 1 and get a tails. I could do a 2 and a heads, or a 2 and a tails, 3 and a heads, or a 3 and a tails, 4 and a heads, or a 4 and a tails, 5 and a heads, or a 5 and a tails, 6 and a heads, or a 6 and a tails. Okay, so as I look at this, I have 2, 4, 6, 8, 10, 12 outcomes here. So 12 possibilities. If we talk about it in terms of the counting principle that we did yesterday, rolling a die has 6 outcomes, tossing a coin has 2. If I multiply 6 times 2, I get 12. It's kind of back to the counting principle. They're just asking you to list the sample space instead of just using the counting principle this time. So take a look. Find the probability that it's both an even and a tails. So even and tails. Now here's what I'm going to do. I'm going to do purple for this one, and I'll change my color as I go along. Even and tails says 2 and tails, 4 and tails, or 6 and tails. So 3 out of the 12. You should always reduce your fraction to 1/4. Let's do another color. Second one, find the probability that it's even or odd. Okay, well, this is odd, this is even. This is odd, this is even, odd and even. So 12 out of the 12 are both even or odd, which is 1. What this means is it will always happen, because what it's saying is basically 100% of the time you're going to get a number that's both even or odd. Okay? I'm going to change my color one more time. Let's look at the probability that it's even and a 7. Okay, well I have these even ones, but I don't have a 7 as any possibility. So my probability is 0, which means it will never happen. Nothing on here is a 7, so it's not a possibility. Okay? So the idea that you're talking about probability is the event is the likelihood that it will occur. And we go like this. The probability of our event happening, and your book describes it like this. The number of events possible out of the number in the sample space. So this is the events you want divided by the sample space. And I'm giving you the formula that they give you. I think overall, though, you know what probability is, but I just at least want you to see their wording as to what it looks like. Let's take a look at the next example. You toss a die 2 times. What's the probability that the sum of the numbers is 7? Okay, so let's list the ways to get a 7. Now, if I'm tossing a die 2 times, let's talk about the outcomes. And I'm going to start here. When I look at my outcomes, for my first die, I have 6 possibilities. For my second time of tossing it, I have another 6. So I have 36 possible outcomes. Now let's talk about the event that I want. How many ways can I get that event? Now, this is one of the things that we did yesterday where we did the sum of two die, so I just want to talk about in general. I could have a 1 and a 6, or a 6 and a 1, and they count those different. I can have a 2 and a 5, or a 5 and a 2. I can have a 3 and a 4, or a 4 and a 3. And so as I look at this, there's 1, 2, 3, 4, 5, 6 possibilities for my event. So the probability that my sum is 7 is 6 out of the 36, or 1/6. Okay, so this is my probability. And again, you could go through and list the sample space if you wanted, but I'm going to use a mixture of sample space and a mixture of the fundamental counting principle in order to get my way through this. So let's keep going and try some more probability. Okay, in a Michigan lottery, a player chooses 6 different numbers from 1 to 36. If the 6 numbers match the 6 drawn numbers in any order, that's huge, the player wins. Okay. In any order says we're dealing with a combination. Because the order doesn't matter, we're working on a combination. Okay, now I'm going to put some key information. Only way to win is to choose the 6 numbers, right? To choose, and I picked the word choose because the order doesn't matter. So, and basically we're choosing 6 out of the 36. Okay, so here's how it works. The probability that I win with all 6 numbers is I have to choose all 6 out of the 6 numbers that are winners, and I divide that by, out of the 36, I choose the right 6. Excuse me. So your sample space is 6 numbers out of the 36 possible. The problem is there's multiple ways to win in any order, and so out of the 6, no matter what order, which means combination, I choose all 6 of them. Now 6 choose 6 is 1, and 13 choose 6 is 1,947,792. And so this is my probability. And because they say they don't care about the order, we're talking combinations. Now, if the order were specific, I would be using permutations, but in this case, we're dealing just with combinations. Okay, let's go to the next example. 12 chips numbered 1 through 2 are put in a bag and 1 is chosen at random. What's my sample space? Well, I have the numbers 1 through 12, right? 5, 6, 7, 8, 10, 11, 12. Let A be the probability that you get an even number. Okay, so we're going to talk about even numbers. I have 2, 4, 6, 8, 10, and 12. That's 6 out of the 12 numbers, which then reduces to 1/2. If I change my color so I can do question number 2, what's the event probability that you get a number divisible by 3? Well, 3 is divisible by 3. 6 is divisible by 3, 9 is divisible by 3, and so is 12. So 4 out of the 12, which then reduces to 1/3. Now the question is, what's the probability that they are in A or in B? So basically I just don't want to double count. As I look at this, we have this 2 works for either of them, 3 works for either of them, 4 works for either of them, 6 works for either of them, 8 works for either of them, 9 works for either of them, 10 and 12 work for either of them. If I count those up, there are 8 out of the 12, which reduces to 2/3. And I'm going to talk about the formula we used in Algebra 2 for the OR as well, but if you list your sample space, it's easy enough to just look at them and figure out what you get. Now, 2 events are called mutually exclusive. The word we used in Algebra 2 was disjoint, okay, but they're mutually exclusive if they have no outcomes in common. Okay, so nothing they have is in common if they are mutually exclusive. Now, there are two formulas that we want you to know, okay? And I'm going to do it in terms of a Venn diagram. Venn diagram means that you're dealing with circles that overlap. So I'm going to call this first one event A, the second one event B. If there is an overlap, then that's this piece here in the middle, and that's the probability, and I'm going to use the notation in our book, of the intersection of B. And so this means basically where they intersect or where they overlap. This isn't, this is talking about and, okay? So if we look at it, this intersection is in terms of and the probability that your book gives you is the union of A and B is the probability of A plus the probability of B minus the probability of their intersection. In your Algebra 2 book, we gave it to you like this. The probability of A or B equals the probability of A plus the probability of B minus the probability that it's in A and B. Okay, and again, and or this union or this intersection, again, is where they intersect or where they overlap. Now, what it says is if I add, and I'm going to show you kind of this idea color form, if I add all of A, okay, so that's the red one, and then I add all of B, do you see what I did? I just double counted this region in the middle, and so what we do is subtract that region because I've double counted it, and so the idea is you cannot double count it. So if there is an overlap, you have to get rid of the intersection. Now, if there's nothing in common, okay, let's call this A and call this B, then if I want the probability of A or B, or what we call the union, if there's no intersection, then I just add A with B. Because they have nothing in common, so I don't have to get rid of anything. Okay, and in this case, again, I'm just going to write it. The probability of A intersected with B equals 0 because they have nothing in common. Okay, so I just want you to see it in picture form. I hope these formulas look somewhat familiar. Again, formulas are not something we're giving you this section, so just kind of be aware of that. Okay, let's take a look then at the back side. We'll practice a few more. In a standard 52 card deck, what's the probability you get a heart or an ace? Okay, now I'm going to change my color because I'm not a big fan of that. So we have the probability that you have a heart or an ace equals, because it's or, we go the probability of a heart plus the probability of an ace minus the probability that it's a heart and an ace. Okay, so let's take a look. How many hearts in a deck? Well, there are 13 out of the 52 cards are hearts. There are 4 aces out of the deck of 52. But there is one card that's an ace of hearts, which we've counted in both parts. So 1 out of 52 has to be excluded. So as I look at this, my probability is 16 over 52. We want you to reduce that in fraction form. So 4 out of 13. Okay, suppose 3 red chips are numbered 1 through 3 are put into a bag, and 3 blue chips numbered 1 through 3 are put in a bag. 1 chip is selected from the first bag, and then 1 chip is selected from the second bag. Let's list our sample space. Sorry. Okay, so I could have a 1 in blue, and I'm going to just kind of write these out as I go through. I could have a 1 in blue with a 1 in red, a 2 in red, a 3 in red. I could have a 2 in blue with a 1, a 2, or a 3 in red. And I could have a 3 in blue with a 1, a 2, and a 3 in red. And I'll show you that as I'm changing colors. But I could have a 1, and then a 1, 2, and 3, a 2 with a 1, 2, and 3, or a 3 with a 1, 2, and 3. And so I just want to color code this as we're going through. It's easier for me to do it separate. Now take a look. What is the event that the first chip you pick is odd? Well, if I look, the first chip I pick is odd. I have how many outcomes? 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 outcomes. All right. If I look, 1, 2, this one, my first chip is odd, and this one, my first chip is odd, so I have 6 out of 9, which reduces to 2/3. Let me change my color here a second. What's the probability that the second chip is a 3? Well, here's 1, here's 2, here's 3, so 3 out of the 9 is 1/3. What's the probability that I get both the first chip is odd, I'm going to change my color again, that the first chip is odd and my second chip is a 3. So first chip is odd and a 3, here's 1. First chip is odd and a 3, here's 2, so only 2 out of the 9. And I want to talk about how we get that in terms of formulas as well, because I don't always want to have to list the sample space. So let's talk about a definition. 2 events are independent if one event has no effect on the second event. Okay? Now, if 2 events are even, then the probability that I get both A and B to occur is the probability of A times the probability of B. So let me go back up above. If I try that, the probability of A is 2/3 times the probability of B is 1/3. 2 times 1 is 2, 3 times 3 is 9. You'll notice that's exactly what I got. And that's how it works. Now you can write out the sample space or you could learn the formula. It's kind of up to you. Okay? So this is again another formula you should know. I'm going to keep going. In Yahtzee, 5 dice are rolled at the same time. What's the probability that all 5 of the dice are 6s? Okay, let's go with the first dice. If my first die, I want to get a 6, my probability is 1/6. For my second die, which doesn't affect my first, my probability is 1/6. And 1/6 for my third, 1/6 for my fourth, 1/6 for my fifth, and 1/6. Oh, I only need 5 of them. Just got excited. Okay? So if I have 5 of them, here's what ends up happening. I have 1/6 to the 5th power, because I take 6 times 6 times 6 times 6, which is 1/7,776. Okay, because each die is independent, then all I have to do is multiply my events together. Okay, now we want to talk about the other idea of a complement, and the reason we want to use a complement is sometimes it's just easier to do a complement than the actual original probability. So here's what a complement. A complement and the event account for all possible outcomes. And we did complements in Algebra 2 as well. The idea was together a complement and an event make up 100% of the time. So in a picture, here's my 100% of the time. Okay? I have one event, and it doesn't really matter what it looks like, but let's say my event happens about, I don't know, 40% or 50% of the time, 40% of the time. This is my event A. So the probability of event A is here. And this is my complement. We call it A prime. Together, okay, these two add up to be 100%. So this equals 100% of the time. So the way we say the complement is the probability of the complement is 1 or 100% minus the probability that my original event occurred. Now again, this is important for when we're doing, I think the easiest way, a range of possibilities. You know, like an at most or an at least type thing. This is normally the easiest. Let me show you an example. When you're dealing Yahtzee, you know 5 dice get rolled at the same time, right? What's the probability of getting 1 or more? Because I'm dealing with a range of possibilities, it's easier to do a complement. Now let's talk about the 5 dice. If I get my number of 6s, I could roll the dice and get no 6s. I could roll the dice and get 1 6, 2 6s, 3 6s, 4 6s, or all 5 6s, which means a Yahtzee. Now they're asking you what's the probability that all of this occurs. Now you could find the probability of 1 plus the probability of 2 plus the probability of 3 if you wanted. I'm not interested. What I'm going to do is look at, instead of saying the probability of 1 or more 6s, I'm going to say what's 1 minus the probability that I don't get any 6s. Because instead of finding all of this, it's easier to find 1 and subtract it from 100%. Okay, so this is my A that they're looking for. No 6s means A prime. So let's take a look at this. How do I find the probability that I don't get any 6s out of the 5 rolls, or the 5 dice, right? Well, the probability that my first dice is not a 6 is 5 out of 6. Because 1 out of 6 is a 6, like we said up here. Times, what about my second die? 5 out of 6. My third die is 5 out of 6. My fourth die is still 5 out of 6. And my fifth die is 5 out of 6. So this really, to save us some time, is 5 6 to the 5th power. So if I want the probability of 1 or more 6s, I'm going to take 1 minus 5 6 to the 5th power, which ends up being 4,651 over 7,776. Okay, this is the probability that I'm going to have 1 or more 6s. And it's so much easier to get rid of no 6s than it is to find the probability of 1 6 plus the probability of 2 6 plus the probability of 3 6 and add them all up. Okay? And this is the idea of when you would want to use a complement. So overall, this section has some formulas to it. We talk about listing sample space, but most of this should be a review from Algebra 2. So what a way to end pre-calc, huh? Enjoy the last video.